Organic Chemistry students, spring 2020. This video is the beginning of chapter 21 on the acid derivatives. So let's start with an introduction about what acid derivatives actually are. And a very simple definition is that all acid derivatives can be hydrolyzed to yield the parent acid and another compound depending on what kind of acid derivative it happens to be. And so the first equation there is the most general form where an acid derivative adds an equivalent of water, probably has to be heated up, but not necessarily in every case, to yield the parent carboxylic acid plus another compound, here just symbolized by the two question marks. A somewhat more specific form is seen in equation 2. Now, the majority of acid derivatives look like this generalized structure, with some R group and a carbonyl that comes from the carboxylic acid, and then a generalized derivative group symbolized by Y. This structure will add water, again, maybe needs heat, maybe doesn't, to yield the parent carboxylic acid, and in this case, HY. So you see that the group that makes the derivative will pick up one of the hydrogens, net from water, or you can look at it stoichiometrically, a hydrogen from water, and the OH from water went onto the carboxylic acid. And so it is the CY bond that is broken in the course of hydrolysis, the OH from water going to form the acid, and the remaining hydrogen from water going to make HY. There is an exception, and that would be nitriles, which need to add 2 equivalents of water in order to be balanced and yield a carboxylic acid plus ammonia. And so, of the 2 equivalents of water, both oxygens went into making the carboxylic acid, and the 4 hydrogens from the 2 equivalents of water, 3 of them paired up with the nitrogen to make ammonia, and the 4th to form the carboxylic acid. There are 5 general classes of carboxylic acid derivatives that you need to know about, and they are listed here in this table. So you see in the left column are the Y groups, and on the right column are the general names that correspond to the particular Ys. And so the first one are the halides. There are 2 halogens that you see most often, and they are chlorine and bromine. And the most general name for this class of acid derivative is, of course, acid halide. But since chlorine is the most common, followed closely by bromine, but chlorine is definitely the most common, it's usually more convenient to just talk about acid chlorides. If bromine happens to be involved, it would be an acid bromide. Note that the anion name is used for the halogen, so it's chloride and bromide and halide as the general name. A second class of derivative that you'll see frequently are the esters. And esters are when the Y group is an alkoxy radical. And so you see that represented by OR. Notice in the parenthesis it states that R cannot be hydrogen. And I hope that's obvious to you. What would you have if R is hydrogen? Let's think about that a moment. Would it not be a carboxylic acid? And so this is the one case where R can't be a hydrogen among the acid derivatives. Now also notice that under the general name where it says esters, there are also cyclic esters, and those compounds are generally called lactones. The Y group could contain a nitrogen, and remember that nitrogen is a trivalent atom, and so if one of the bonds to the nitrogen is taken up by being bonded to the carbonyl, that leaves two valences that need to be occupied by something. So in this case you see it's written as NR R prime, and in parentheses it says that R can be hydrogen, an alkyl group, or an aromatic group. R and R prime could be the same group, that is, it could be two hydrogens on the nitrogen, could be two alkyl groups, perhaps methyls, or R could be a hydrogen and R prime could be a methyl. So we can mix it up a little bit there. Now notice in the general name, these compounds, first of all, are referred to as amides, and they also can be cyclic. And when they are cyclic, they're referred to as lactams. The Y group could be a carboxylate. It's a little difficult to write that using letters on the keyboard, but that would be from the parent acid group, R carbonyl, then the bond, the Y group, is a single bonded oxygen that is bonded to a carbonyl. On the other side of that carbonyl is an R group. And so that is actually another acid group. It's a carboxylate. And I didn't put it there in parentheses, but that R could also be a hydrogen or alkyl or aryl. These are the anhydrides. Notice under anhydride it says there are many more, and indeed there are. There are a great number of acid derivatives. We don't need to survey them all. We do need to survey these four, especially the esters and the amides, because they show up in other classes like biochemistry and perhaps a few biology courses. And then lastly, I'll mention the nitriles. Now in the case of the nitriles, the Y group is not a typical Y group. Notice that it is C triple bond N, although the triple bond is implied. Again, some things aren't so easy to write with a keyboard. And these compounds are referred to as nitriles. We need to know how to name these derivatives. And so let's start with esters. The pattern for all of these names begins the same way. You have to be good at naming the acid, the parent acid from which the derivative comes. In this case, the ester. So notice what it says first of all in parenthesis beside esters. Always begin with the parent acid name, drop the IC, add ATE. And so in the first example, think about that structure. And on the left-hand side, the parent acid, which would always be the part that contains both oxygens, must be benzoic acid. Dropping IC and adding ATE leads to benzoate. Then add the alkyl name and put it in front with a space. In this case, the alkyl group attached to benzoic acid is an ethyl, and so the final name is ethyl benzoate. Here are two other structures, and it would be good for you right now to pause the video and try to name both of these compounds. Again, separate out the parent acid. Think about what the parent acid name should be. Then modify that from the IC ending to ATE. And then think about what the alkyl group's name should be. And put the alkyl name in front of the modified acid name to come up with an answer. This is just in case you decided to flip forward anyway and cheat and see the answers without working on them. But seriously, folks, and these are the answers. So if you look at the parent acid, if you didn't get this one, think about what you did wrong. It is a 4-carbon acid, so that was butanoic acid. That becomes butanoate. Now, the butanoic acid has a chlorine substituent on carbon 3, so 3-chlorobutanoate. The alkyl group attached, of course, contains 3 carbons. It's attached from the terminal carbon, so that would be propyl. The second compound, now notice that the acid group has been flipped around, so the acid is actually on the right-hand side. I do typically put the acid group for an ester on the left-hand side of the structure, but not always. So in this case, the acid is on the right-hand side, and that is a 5-carbon acid, right? And so that makes it pentanoic. The methyl group is attached to carbon number 4, so it's 4-methyl pentanoic acid. Drop IC, add ATE. Now, in this case, there's a bromine attached to the alkyl group, and so that becomes 2-bromopropyl. So when you're naming esters that have halide or other substituents on either the alkyl group or the acid group, make sure that the substituent on the acid remains with the acid name. Like in the first one, it's chlorobutanoate. And if the substituent is in the alkyl group, then make sure that stays with the alkyl name, like in the second structure, and bromopropyl. Onward to a couple of other names. Recall that carboxylic acids sometimes have 2 acid functional groups, and so if there's an ester of a diacid, the pattern has not changed. It's still the same. You can use either IUPAC or common names. In this case, I don't care. In fact, the common names of the shorter chain diacids are actually quite a bit more common. And you should know them, or at least know where to find them if you need to. And so the structure on the left, if you're stuck, you can always go with systematic nomenclature. It's a 3-carbon diacid, so it's based on propane, but don't forget the di. So propane dioic acid would become propane dioate. What's attached as an alkyl group is the same on both sides, so remember that it should be dimethyl propane dioate. The common name for propane dioic acid is malonic acid. As I say, you should be aware of the common names for the shorter chain diacids, or know where to find it. I'm sure you could Google names of diacids and find a wiki page that has them listed out and just be able to find that again. So the pattern is the same though. Malonic becomes malonate, and still 2 methyl groups in front, so dimethyl malonate. Now notice though, malonate comes from malonic, and malonic is the common name of a diacid, so you don't need to put diate in there. It's just malonate. And here again are 2 other compounds to try. The 2-carbon diacid and the 4-carbon diacid, both of them as esters. And again, try to name these on your own before you move forward. Pause the slide, in other words. And yeah, did you even bother? Come on now. You should practice. One last thing with regard to esters. They also appear as cyclic structures, in which case they are called lactones. Now the nomenclature for lactones, I'm going to simplify it a little bit because After organic chemistry, if you see lactones again, it's probably going to be in the context of a larger molecule. And so I only want you to really notice what lactones are and how to refer to them generally. Let's start with the lactone on the left. Notice that the lactone is a 5-member ring with the oxygen of the ester incorporated into the ring. So that's an important feature. Now, as far as the nomenclature for this compound, it's easiest to deal with it generally as a lactone. And we have to think about the attachment of that oxygen. And so I want you to, first of all, think about the acid from which this ester would come. Obviously, if the oxygen is part of the ring, and if you were to subject this particular lactone to hydrolysis to see the parent acid, the oxygen that is part of the ring would simply open up. The bond that's broken is only the bond between the oxygen and the carbonyl carbon. The other bond, the oxygen to the CH2 carbon that's part of the ring, that bond remains firmly in place. And so when this compound is opened, notice that the OH is still part of the parent acid. So this is a compound that generally would be referred to as an hydroxycarboxylic acid, or often just simply hydroxy acid. If you were to name this compound, I trust you would come up quickly with 4-hydroxybutanoic acid, because the hydroxy group is attached to the 4th carbon. If you were to think about common nomenclature, again, sometimes the shorter chain carboxylic acids are known by their common name more frequently than they are by systematic nomenclature. And I think the 4-carbon carboxylic acid is a case in point. A lot of people, myself included, still refer to it as butyric acid. If you're going to call the compound by its common name, butyric acid, then the substituent gets a Greek letter instead of a number. And so, in terms of Greek letters, this would be the gamma position. The carbon right next door to the carboxylic acid group is alpha, the next one's beta, the one after that is gamma. So it's gamma hydroxybutyric acid. And that's partly why it's referred to as gamma butyrolactone. It's a nice, easy general name for this compound, or simply a gamma lactone. And you could follow the Greek letters around the ring in this case, but you would go counterclockwise, starting with the carbon of the carbonyl, and so the one next door is alpha, then beta, then gamma, and that's when you get to the oxygen. So that's really the reason it's a gamma lactone, but it does come from a gamma hydroxy acid. It would be true that all gamma lactones are 5-membered rings, even if they have other groups attached to the carbons that are available for attachment. Let's consider the lactone on the right, which still comes from a butyric acid, but now it's a beta hydroxybutyric acid, right? The hydroxy group is on the beta carbon. And so when that ring closes, it forms a 4-membered ring, as you can see in the lactone. And that means that the methyl group is attached to the 4-membered ring, since it was attached to the original acid. And so lactones can have alkyl groups attached to the ring. They would be part of the original acid. This is an example of a beta lactone, beta butyrolactone. All beta lactones would be 4-membered rings. I added the true systematic names for both of these lactones. And so you can see how complicated it can be. The 5-membered ring lactone, the beta lactone, oxalan-2-one. Imagine if I asked you to name that on the quiz or exam. And the beta butyrolactone, its official name is 4-methyloxetan-2-one. And so the official names become a little bit more difficult to derive, and I don't think it's important. As I said, what I want you to remember is that it's a beta lactone or a gamma lactone. What if it happened to be a larger ring or even a smaller one? Well, again, the Greek letters are what we use, and you see them on the screen. In case you don't remember the first 5, they are there. You really should remember the first 5 because they do appear in nomenclature in different scenarios. And so alpha, beta, gamma, delta, epsilon. If you can remember those, wonderful. The only other Greek letter that you really should remember is omega. And omega simply means last in the context of nomenclature and in a few other contexts. Easter's come, and some of you may be familiar with the alpha and omega, which means first and last, by the way. Continuing on with naming, let's take a look at acid halides. They're pretty simple. You drop in the IC, adding YL and the halide name. Remember, it's the anion name of the halogen. And so the first example, you look at that and you say, I recognize that acid, it's acetic acid. And so the IC gets dropped off, add on the YL, that becomes acetyl or acetyl. I've heard it pronounced both ways by different people. I'm not going to be fussy. We're probably not going to be talking about this in person. You need to be able to write it. And then add the halide name. So acetyl chloride. You could also go with the systematic name. I don't care, especially if you don't remember the shorter chain names. But acetic acid, pretty much everybody knows. But ethanoic, and notice what happens. I didn't point this out with esters, but notice what happens because it is just the IC. You're not dropping the O. So ethanoic becomes ethanoyl, and the halide name goes after that, ethanoyl chloride. And I give you one here to practice as well. I didn't put in a slide, so you can just move on if you want to, but you should try to come up with that name. So pause the video and ask yourself, what would be the name for this compound? And so here are the names. Notice I have 3 options now for the name for this particular acid, chloride. It's a benzoic acid derivative. Notice that there's a methyl group attached to position 4 with regard to benzoic acid, and so that is why it's 4-methyl-benzoyl chloride. Because it's only one group attached to the benzoic acid, you could also use para-methyl-benzoyl chloride. Probably few of you remember that that particular acid, 4-methyl-benzoic acid, has its own common name, toluic acid. And so you could call it toluyl chloride. There are 3 isomers of toluic acid, so you have to put in the para. Don't use 4. It wouldn't be appropriate because ortho, meta, and para belong with the monosubstituted common names of benzoic acids. So para-toluyl chloride. A little bit of a tongue twister. Naming anhydrides. Uber simple. Yes, I said that. In this case, you just take the names of both acids and add anhydride afterwards. And so you take a look at the first compound, and I hope you recognize again that that's acetic acid that goes into making that anhydride. So two equivalents of acetic acid come together. An equivalent of water is lost to make the anhydride. Remember, we looked at that particular reaction at the end of the carboxylic acid chapter. And simply put, this is acetic anhydride. So in the second example, you look at it, I hope you recognize that benzoic acid is present. And the other side, the right-hand side, that's propanoic acid. So option number one is benzoic, propanoic, anhydride. Notice it's three words. Don't smush this together. Wouldn't be prudent. Here again, I think you should at least know that the smaller acids have common names, although I don't know many people who still call this particular acid by its common name. So benzoic propionic anhydride. Interesting oddball trivia. Propionic is derived from the Greek, which means first fat. And then you can also find anhydrides that are made from diacids. They have to be the right size most of the time. Remember that closing to form 5, 6, and 7 member rings is relatively easy. And so this could be called phthalic anhydride. That is the common name. If you're stuck with these common names, just go with the systematic. If you think about the acid from which that anhydride comes, I hope you would determine that it would be called 1,2-benzene dioic acid. And so 1,2-benzene dioic anhydride is the appropriate name. Continuing on, amides. Pretty simple. Drop the IC or OIC this time and add amide. Okay? The first one comes from benzoic acid again. So you're dropping the OIC of benzoic acid to make benzamide. Notice that it is a primary amide. Why is it a primary amide? Remember that when nitrogen is involved, primary, secondary, and tertiary actually refers to the nitrogen and not to carbons as in the case of other functional groups. The nitrogen has two hydrogens on it. That's what makes it a primary amide. The second structure comes from formic acid or methanoic acid if you don't remember that it's formic acid. And so formamide, if you didn't remember that, it's a single carbon acid, and you really need to remember that that is methanoic acid. Notice that in this particular case, the nitrogen has two methyl groups attached. So you have to formally say that. It is dimethylformamide. Now notice in front of the dimethyl, I have two capital italicized N's. When substituents are attached to nitrogen, in the case of organic compounds, we use a capital italicized N to specify where the substituent is attached. Numbers tell us where a substituent is attached relative to a carbon skeleton. So when nitrogen is involved and there's a substituent attached there, we use a capital N. And you'll see that throughout organic compound nomenclature. Because this nitrogen has two alkyl groups attached, it represents a tertiary amide. Again, primary, secondary, and tertiary relates to the substituent pattern on the nitrogen, not carbon. And so last but not least, the structure that's on the right, N-ethyl acetamide, an example of a secondary amide. Again, you see that capital italicized N preceding the ethyl, and so that lets us know with certainty, if all you saw was the word, that the ethyl group is attached to the nitrogen. Remember that amides can also be cyclic. When they are, they're generically referred to as lactams. And so in a similar way to lactones, we refer to them as beta-lactams or gamma-lactams or delta-lactams, depending on how big the ring is. Like lactones, beta would always indicate a four-membered ring with the nitrogen incorporated into the ring. Now with a hydrogen on that nitrogen, there could also be an additional substituent on that N. So be aware of that. Think about the amino acid that would make this lactam. I'll let you do that on the side. I don't have that on a coming slide. And as a side note, beta-lactams were very important in the structure of penicillins. Notice the penicillin structure here is a generalized form. There's an R group on the left side of the structure, so that R group can be different types of alkyl and aromatic and other things attached there. Last but not least, nitriles. I didn't put in parenthesis the key to naming nitriles, but it ought to be pretty obvious. You're dropping the IC and adding nitrile, and that's all there is to it. So in this example compound, when you look at a nitrile, consider the carbon of the nitrile as part of the parent acid. So you're looking, in this case, at another benzoic acid derivative. That benzoic acid would be 3-methyl benzoic acid. So we're dropping the IC, adding nitrile, and it becomes simply 3-methyl benzonitrile. The final topic, naming priority. This is it. This is the final order of nomenclature. I don't think we'll get to anything else this semester. And so, for compounds that have multifunctional groups, like the ultimate name that I have here on the slide, the priority is, if there is a carboxylic acid, it precedes everything else. And the order after that, you see that. I don't really need to read it, but I feel somehow compelled. So acids come before anhydrides, which come before esters, which come before acid halides, which come before amides, before nitriles, before aldehyde, before ketone. And I didn't put alcohols up there, but that would be the next one. And then after that are all the things that just sit around. Nitro, alkyl groups, halogens, what else? Ethers, yeah. And so you look at this compound with its ultimate name and you give it a quick survey and you see 4 acid derivative groups are attached to an aromatic ring. This compound is out of your textbook. And so think about which groups are actually present. And of course there's a carboxylic acid, there is an ester, there is a nitrile, there is an acid chloride. And so the carboxylic acid present wins. So the parent name for this compound is benzoic acid. And the rest of them are all named then as substituents. So what are the substituent names for each of them? So let's start by reading from left to right across the name. Chlorocarbonyl. That is the substituent name for the acid chloride. I think the textbook uses chloroformyl, but that's okay. Chlorocarbonyl. The nitrile group is referred to as cyano, as a substituent. Cyano comes from cyanide, so that is the substituent name for a carbon triple bond N. The ester is called methoxycarbonyl. So think about that for a moment. What if that were an ethyl group instead of a methyl? And how would that substituent name change, right? That would become ethoxycarbonyl. If that were a propyl ester instead, propoxycarbonyl, right? So they are the substituent names. Now that actually only took care of the ester halide, and nitrile. The amide is not included in this particular name, neither is the anhydride, nor are aldehydes or ketones. They are in the textbook, I believe, though, so I refer you there. And then, of course, the numbering around the ring would be based on the fact that it is benzoic acid as the parent name, so the carbon to which the acid group is attached must be number 1, and then go clockwise or counterclockwise around the ring as always, noting the first lowest number. And so going clockwise gives you 1, 2, 4, 5 as the substituent positions. If you went counterclockwise around the ring, you'd get 1, 3, 4, 6. And so 2, 4, 5 wins. And thus it ends. Thank you for not paying attention.